So today I'll start talking about paths. So if you recall from yesterday's broad motivational lecture on why we want to do this, our objective is going to be to develop some combinatorial object which is an analog of Tableau. Okay. Just like Tableau give you formulas for weight multiplicities and so on and so forth, this object paths will do the same thing and also in a uniform manner. It will do it for all semi-simple D algebras, the affine algebras and so on. Okay, so it's a very sweeping generalization of Tableau, but so you will have to bear with me for quite a bit. So it's not going to look anything like Tableau for a very long time. So for now, just play along and let's just try to understand what the definition is and what the properties are and so on. So just keep in the back of your mind that at some point we'll see that these things are actually Tableau in the case of SLN. Okay, so so for now I'm going to, so unlike yesterday, I'm now going to make this slightly more general. So I'll say any finite dimensional, say simple Lie algebra, okay, of which SLN is one example, and a lot of the stuff we saw about SLN yesterday works in general, works in this context. So in particular, the Lie algebra has a root space decomposition, which has this form, which means just like the diagonal matrices, you can always find some subspace, subalgebra, which is an abelian D algebra, which means the commutator on H is 0. So this is what's called the Cartan subalgebra. Okay, it has the property that any two fellows coming from the Cartan commute. And these spaces, just like in the case of SLN, are one-dimensional spaces. So they're all one-dimensional. So these are what are called root spaces. And the property they have is that they are eigenvectors for the adjoint action of the Cartan on the Lie algebra G. In other words, if I take an element from G alpha and take an element from the Cartan, the commutator H comma X will give me the same multiple of X, but the multiple, the eigenvalue is given by this linear functional alpha. Okay. So to tie this in with the SLN situation, this is the space of trace zero diagonal matrices, and in that case the set of roots delta was exactly the epsilon I minus epsilon j's, right? That was what we had looked at yesterday. Okay, so just for, so if this general setting is making you uncomfortable, just replace G. Anytime I say G, just think of SLN, think of the set of roots as just epsilon I minus epsilon j. So this is for 1 less than equal to I not equal to j, and H is the space of diagonal matrices and so on. Okay, and among the set of roots, we also mentioned the simple roots, so they are now important for us. So the simple roots in this case, so let's denote alpha 1, alpha 2. So in general, there will be some L of them. In this case, L is n minus 1. So these are, let these be the simple roots of G. So again, let me say what it is in the case of SLN. These are just epsilon 1 minus 2, so the successive differences 2 minus 3 and so on, n minus 1 minus n. So there are exactly n minus 1 of them. So in this case, the number L, which is the number of roots, is just n minus number of simple roots. And corresponding to each of them, we said, or more generally corresponding to any root, we had constructed an SL2C, and here I'll now say alpha 1 check, alpha 2 check, alpha L check are what are called the simple co-roots of G. So what are these? Well, the alpha i's are all elements of H star. They all belong to the dual Cartan because they are the eigenvalues, whereas these guys actually belong to the Cartan itself. They are all elements of H. So what are they? They are exactly the elements which you get when you form those SL2s out of each one of these roots. So in this case, in this example, for this simple root epsilon 1 minus 2, the corresponding co-root is E11 minus E22. For this guy, it's E22 minus E33 and so on. En minus 1, n minus 1 minus En. Okay, so this is the example. Sorry, I forgot to say. So all this is for SLN. Right? So the simple co-roots are the corresponding elements of the dual of the Cartan subalgebra obtained when you form the SL2 starting with that root alpha I. Okay. Now we also defined the space P, the weight lattice last time. The weight lattice by definition is all those elements of H star, the dual Cartan, such that lambda evaluated on each of these. So this is an when you evaluate lambda on each of the simple co-roots, what you get is an integer. Okay. In the general case, yeah, sure. Okay. So what we did in the case of SLN, we just replicate that. So what is a simple co-root? We need to start with G alpha. So G alpha, he said, is a one-dimensional space. So in particular, I can look at G alpha I, the ith simple root. I look at the corresponding root space. I also look at G of minus alpha I, okay, the corresponding negative root space. So what did we do last time? We said you take an element here, you take an element there. Now between them they don't form a subalgebra, right? If you take the Lie bracket of these two things, it's not again in the same thing. So the Lie bracket of these two guys turns out to be an element which lies in the Cartan subalgebra. Okay, so the Lie bracket of G alpha I and G minus alpha I turns out to be a one-dimensional space. It's a one-dimensional subspace of the Cartan. So that element, so direct sum, so G alpha I, G minus alpha I, and there is one additional element which I'll define in a moment. So that's going to be the co-root C alpha I check, which has the following property that if you take these three guys, you take an element x here, you take an element y here, and you take that element alpha I check, then these three form the standard basis for SL2. So okay, x, y and alpha I check, if you write out the commutation relations, it will turn out that it's alpha I check bracket with x is 2x. Okay, so similarly alpha I check bracket with y is minus 2y. And there is some scaling involved here. You have to scale x and y appropriately so that their bracket exactly gives you alpha I check. Okay, so you can always find, you know, these elements. In particular, the alpha I check is sort of uniquely defined. It's that exact element in the Lie bracket of these two spaces, which satisfies the property that alpha I evaluated at alpha I check is 2. This property uniquely determines it, and that's required because of you need to get these eigenvalues to be 2 and minus 2. In order for these to work out to be 2 and minus 2, you need to have this additional condition. Okay, fine. So sorry, I'm just giving you a very brief overview of this. So that's how the co-root is defined in general. There's always an SL2, and it's sort of the H element of that SL2. Okay, so that's called the weight lattice. And we also talked about the set of dominant weights last time. We said it's all those guys for which this is. So it's also defined this P plus is all those elements of the weight lattice where this number is also positive. So yesterday I had defined this a little bit differently. I said for all, not just the simple roots, simple co-roots, I said for all alpha checks, right? I said for all EII minus EJJ, it needs to be true. Okay, that's too much. You don't need that. It's enough to ensure it's true on the simple co-roots. So this was a space of dominant weights. This is the weight lattice. This is a set of dominant weights. Okay, so we are, I guess we have all the initial data we need to start talking about the paths themselves. So here are some definitions. So let's call, so paths are going to be paths in the usual sense of the word. They are continuous, maps from the interval to the space H star. So the paths are going to be paths in H star. So really, that's what we're going to look at. So let's consider the interval 0, 1, but for pretty much everything we'll do, it's not necessary to look at all the real numbers. We'll only restrict ourselves to the rational numbers in the interval 0, 1. Okay, so I'm redefining this symbol 0, 1 for us will always mean the set of rational numbers inside 0, 1. Okay, because everything we talk about really will require rationality in some sense. So it's most convenient to just redefine it in this way. So 0, 1 is this, and let me take P, which is the weight lattice here, and let me define P sub Q. This is again the rational version. It's just the Q span of P. Okay, so think of this as sitting inside H star. Okay, so this is just the Q span of P. So P in general will, here's sort of one picture to keep in mind. So if this is your space H star, two-dimensional space, okay, which it will be in the case of SL3 for example, then the weight lattice is some lattice. So imagine for the moment it's say some lattice like this. So it's just some grid in this sense. So this is a picture of P for example. Okay, then when I say Q span, it's just it's all Q linear combinations of this. So I won't get all of H star, but in some sense the only things that matter to me are things which can be obtained as rational combinations of weights. Okay, so all this is just you can broadly think of it as we really want to do stuff in all of H star, but what's relevant always is only the rational things. So we just restrict ourselves to the rational bits. Okay, other than that there is no big this is not some very major subtle point or anything you need to worry about. This rationality is just for convenience in some sense, in building it into the definitions. Okay, now so what's going to be the set of paths? So let me define the paths for the first time. So this is the set of all paths pi. So let pi denote the set of all paths, by which we mean pi, so small pi function from 0, 1 to PQ. So this is a path for us. Okay, a path is just a function from the rational numbers in 0, 1 to the Q span of the weight lattice, satisfying the following condition, that it is piecewise linear, satisfying the condition that, well, it starts at the origin, pi at 0 is 0 and pi is piecewise linear. So what does piecewise linear mean? It says that I can divide my interval into finitely many pieces, and since of course everything is really rational, I should say piecewise linear just means the following thing for us. Means there exist rational numbers, let's call it T1, T2, TR, in between 0 and 1. So think of it as TR1. So they divide the interval 0, 1 into R segments in some sense, right? R or R plus 1, R plus 1 segments, I suppose, right? So the way I've written it, 1 is the R plus 1th guy. So they divide it into R plus 1 segments, and what else? So there exists rational numbers. So I should say there exists Ti. There exists Ti in Q satisfying this, and such that on each segment the path is just a linear thing. It's just a straight line path like this. Okay. So imagine this is now I'm drawing a path somewhere on the plane. So what's a piecewise path? It just starts at the origin, okay, and goes to some. So these are the different pieces of the path, for example. Okay. Of course, the point is it should be piecewise linear. So I want the path to be a map to PQ. So at every rational time, every rational value. So this is the first breakpoint. Let's say at T1, I want this point to be something which lives in the rational span of the weight lattice. Okay. So imagine a path like this. So here's mu1, which is some element of PQ. And then from time T1 to T2, the path again is just a straight line. So at time T2, it reaches some point here. So let me call this point mu1 plus mu2. So mu2 is the increment. Mu2 again should live in PQ. Okay. Only then this mu1 plus mu2 will be an element of PQ. And then again until time T3, it travels in a straight line and reaches some other point. So let me call this mu1 plus mu2 plus mu3, and so on. Okay. So this is basically what a path is going to be. So here there are some time stamps T1 to TR and elements mu1, mu2, mu r plus 1 in PQ, such that the path has the following form: pi of t. So I have to define it piecewise. So when t lives between 0 and T1, it's just a straight line which ends at mu1. So I need to do a little bit here. It's so what's a straight line which ends at mu1? This is t by T1 of mu1. Okay. So I mean when you write it down as formulas, it's always much hairier than it really is. So I just mean that mu1 is where it ends at time T1. Then I go from T1 to T2. So what's the equation of a straight line path from T1 to T2? So at time T1 it is at mu1 plus it travels between time T1 and T2 and reaches mu1 plus mu2 at the next time, right? Is this formula okay? So at time T2 it reaches mu1 plus mu2 and so on. So maybe I'll write one more, mu1 plus mu2 plus between timestamps T2 and T3, this is mu1 plus mu2 plus t minus T2 by T3 minus T2 times mu3 and so on. Is this fine? Is this definition okay? So this is just a sequence of segments which the first segment goes from 0 to mu1, the next segment is between mu1 and mu1 plus mu2 and so on. where all these mu increments mu1, mu2, mu3 etc. must all come from PQ. Okay. So this is basically it. This is going to be the set of things we look at. It has to start at the origin. That's the other condition.
Why is this rational for all time?
What rational?
Why is this rational for
Yes, it has to be, right? Because mu1 is in PQ. Yeah, thanks. That's a good question. Mu1 is in PQ. So now if t is a rational number, so t1 is rational as well. What's rational? T has to be rational, right? No, it won't be rational for all time, of course. T, remember 0, 1 only means rational numbers in 0, 1. Right? So I'm really only defining this for all rational numbers in 0, 1 if you wish. I mean, my new notation 0, 1, which is only the rationals. Okay. So maybe if you wish, this is the usual 0, 1 intersection Q. So for all rational values of t, this path pi t, the value is in fact in PQ, is in the Q span of P. Okay, so that's this formula. Now the point is, in addition, there's one further thing we need to say. We identify two paths up to reparameterization. So we identify paths up to reparameterization. Pi 2 if, so what do we mean by reparameterization? Let me also say this. So we write pi 1 equivalent to pi 2, they are the same path really if they only differ by a reparameterization, which again should be piecewise linear and so on. So if there exists, let me write all the adjectives, piecewise linear, non-decreasing. So piecewise linear, non-decreasing, surjective, continuous, map phi from 0, 1 to itself. So I am reparameterizing the time such that pi 1 is nothing but pi 2 composition phi. Okay, so this is what we usually mean. I mean, without all the adjectives for the moment, this is sort of what you mean by reparameterization, right? You let the time be traversed in some other fashion. Okay, but as long as the final path that's being traced out is the same, you want to think of them as really being the same paths. So the additional thing here is we require that this reparameterization map should also be piecewise linear. Okay, so non-decreasing, surjective, continuous, and so on is the usual set of things you require for reparameterization. Okay, so what this really means now, again, without again, not this isn't something that should worry you too much. This just says that any two paths. So a path is really determined once I know what those mu1, mu2, mu3 and so on are. Those timestamps don't matter. Okay, so if I have, so let's say again, let's back to that same picture. So if this is my origin, so if I have a path, so the first segment, it ends at mu1. Say the second segment increment is mu2. So I go to mu1 plus mu2. So let's say this is my path. Suppose it has 3 segments. Mu1, mu1 plus mu2, mu1 plus mu2 plus mu3. Then it doesn't matter. It doesn't matter what timestamps I assign to these. Okay, so I could arrive at so I could travel from here to here in time 1/3, go from here to here from 1/3 to 2/3, then 2/3 to 1. That's one way of traversing it. Or I could go very fast, reach this in very short time, and then go slowly from here to there, and so on. So these reparameterization just sort of say that it doesn't really matter at what times you actually reach these places. It just matters which places you reach. So the final thing that you trace out is what's important. Okay. In other words, just knowing these pi 1 plus pi 2 and pi 1 plus pi 2 plus pi 3, these three things uniquely determine the path. That's all the data there is for the path. But of course, to actually manipulate it, to write down formulas and so on, you need a parameterization. So that's the reason why we sort of define it in terms of the parameterization. But then we throw it out via this equivalence, that two things which are just reparameterizations are considered to be the same path.
So what is the along the x-axis?
No. There is no x-axis. Think of this as the plane. This is a picture of H star. So what I am drawing is a picture of H star.
It's not the t, right?
No, there is no t here. So the t is really the t is a time variable which you just keep track of. Think of it as time changes. Think of it as a particle which is moving. So as t changes, say I reach this point at t equals 1/3, then I reach here at 2/3, then I move and get here at t is not on the picture. Yes. Okay. Just the path traced out by a particle as it moves from time t equal to 0 to t equal to 1. Okay, and again, I mean, in some sense, I should only be plotting the rational points, but since I can't conceivably do that, we're just drawing the whole thing. So the key thing with this rationality is that these turning points, these break points, are all rationals. That's the key thing. This should come from the rational span of the weight lattice. This mu2, the increment, or the whole thing, whichever way you want to think of it, is. This is there. That's the key thing. Okay. So that's my. So in some sense, it's just enough to know these things. That's all. That determines a path uniquely. Okay. So we have paths. Now, what we are going to do is, so these guys will turn out to be the analogs of tableau. Okay. This is where we are eventually going. Now, what we'll do next is to define some operations on paths. Okay, so we need to do something to the paths. So we'll define certain operators on paths. But before we do this, the operators are all going to involve the action of the Weyl group. So let me just remind you what the Weyl group action is. So the Weyl group action. So what's the Weyl group in general? So the with the same notation I had before, G, the finite dimensional simple Lie algebra looks like this. Now we had those simple roots alpha 1 through alpha L. Now each of those simple roots actually defines a certain operator. So corresponding to alpha I have an operator called Si, and that operator acts on H star. Okay, so this is what you would call the ith simple reflection. Okay, corresponding to the ith simple root. And what does the simple reflection do? Here's the definition. It takes any element of H star and it maps it to, so in addition to these, remember I also have the co-roots. So I should always keep track of both at the same time. There are simple roots and simple co-roots. That's the whole package. So what Si does is it maps lambda to lambda minus, lambda is an element of H star, alpha I check is an element of H. So I can evaluate a functional on an element of H. I'll get a complex number times alpha I. This is the formula which defines the linear transformation. It's lambda minus lambda alpha I check alpha I. And if you have seen it before, you'll probably remember that this is a reflection, the sense that there is a certain codimension 1 subspace that's preserved, that's pointwise fixed by this reflection. So there's a certain mirror, you think of it as a reflection about some hyperplane. The hyperplane is exactly all those functionals which vanish on alpha I check. Those guys are pointwise fixed by this Si, and alpha I, which is, so think of alpha I as being this vector. Alpha I doesn't belong to this the hyperplane, but alpha I is mapped to minus alpha I. So this is what Si does. It takes alpha I to minus alpha I, okay, and it pointwise fixes the hyperplane which vanishes on alpha I check. Okay, so that's one way to think of Si. It's just a reflection. So in particular, if you do it twice, so this is just reflection about that hyperplane, so you do it twice, it's just the identity. Okay, so that's what the, I mean, that's how you define the simple reflections, and the Weyl group itself is just the subgroup inside the general linear group of H star. So all invertible linear transformations on H star, invertible linear operators on H star, generated by these L linear operators, by these simple reflections. Okay, whatever you get, it's a group generated, and whatever that is, that's called the Weyl group. And in the case of SLN, so just to sort of match everything up with our familiar example, so in the case of SLN, here's what it is. Example, let's just write out these guys in full. So if you remember the alpha I, so what's alpha I in the case of SLN? So I said it's epsilon I minus epsilon I plus 1. Alpha I check is the diagonal matrix EII minus EI plus 1 I plus 1. And that's all you need really to figure out what SI does. Right? You need to know what the ith root is and the ith co-root is, ith simple root. So how does SI act on an element lambda? Well, it just maps it to, well, we have the formula. So in particular, let's see what it does to epsilon j's. Okay, so SI will act on any element of H star. In particular, the epsilon j's, if you remember, they span the space H star. Right? So let's compute the value of the action of SI on epsilon j. By this definition, it's epsilon j minus epsilon j evaluated at alpha I check, alpha I. Okay, alpha I is of course epsilon I minus epsilon I plus 1. And alpha I check, I need to replace it with this diagonal matrix. So what's this diagonal matrix? So let me just write out the matrix itself. It's got a 1 in the ith position and a minus 1 in the next position, I plus 1. This is what the diagonal matrix looks like, right? And now I'm going to evaluate epsilon j on that. Epsilon j by definition is, it gives you just the jth diagonal entry. Okay. So epsilon j is almost always going to give you 0, because except for these two fellows, everybody else is a 0. So epsilon, this term here is always almost always a 0. If j is not I or I plus 1, it's a 0. If j equals I, then epsilon j acting on this diagonal matrix will give me a 1. So it's epsilon, and so if j is I, it's epsilon I minus of epsilon I minus I plus 1. So that I is cancelled and I get I plus 1. So this is if j equals I, and if j equals I plus 1, it's epsilon I plus 1 minus of, this is now a minus 1 acting on that guy. So that's going to give me minus of minus 1 plus 1, that's an epsilon I. Okay. So the first thing we notice is that what this simple reflection SI does is that it permutes the epsilons amongst themselves, the epsilon j's, but it's actually a very simple thing. It's just the simple transposition. It just interchanges I and I plus 1, right? Epsilon I goes to epsilon I plus 1, epsilon I plus 1 goes to epsilon I, all the others are left unchanged, right? So this is just a simple transposition, and in this case, therefore, the Weyl group is just a symmetric group with the simple reflection acting as just the ith simple transposition. Okay. Okay, so this is useful and important to keep in mind, because a lot of these operators that I'm going to define on paths will involve the Weyl group action, and so in order to actually see it in a proper example, we'll take recourse to the SLN case, where it's very easy to describe. The reflection will just swap I and I plus 1. So you need to keep that in mind. Okay, and we have defined what the simple reflection does to a given element of H star. So I've just said SI lambda does that. More generally, if I give you a path pi, so if pi is a path So pi belongs to this set capital pi that I define. So if pi is a path, I can define the simple reflection acting on the path to just be the pointwise simple reflection. So how will I define Si on a path? Its value at time t is just the simple reflection applied to the path at time t. Okay, this is the most obvious thing we can define. So in particular, it means, for example, if I have a path like this and say I am interested in trying to reflect, so maybe reflect the whole path, I need to apply an Si to the whole thing, I'll just figure out whatever it is. If say this is the hyperplane about which I'm reflecting, so let's say Si does that, it's just a reflection. It'll take this, it'll map it to whatever. That will be the image of this path under this simple reflection. Okay, the whole path has to be reflected. Fine. So that's my action on paths. Now, what else can one do? What are the operations on paths? The most obvious one is concatenation. So this is the reflection operation. This is a reflection. So all these are on paths. So what's concatenation of paths? If I have two of them, pi 1 and pi 2, I'll define pi 1 star pi 2 in the obvious manner. I'll first traverse pi 1. So one way of writing this is to say between half and half. Okay, this is a formal way to write it out, but what this says is if you have two paths pi 1 and say pi 2, so this is the endpoint of pi 1. So this concatenation is just you traverse pi 1 first and then you traverse pi 2. Okay, the order is important, meaning by this I will always mean pi 1 is being traversed first. In other words, that's the formula. Okay, so that's the concatenation of paths. And again, remember that everywhere I said reparameterization doesn't matter. Okay, so I could have reparameterized this in many ways. I could have written, instead of going from 0 to half, traversing pi 1 between times 0 and half, I could have chosen to traverse it on a longer time interval or shorter time interval and so on. Okay, the basic idea is that this is the actual trajectory that I get. No. That's why the plus. All paths start at the origin, remember. Right? All my paths always start at the origin by definition, right? That was one of the conditions on this. Yeah. So it's not paths which start at any point. Everybody starts at the origin. I'm supposed to move this origin to the end point of the other path. So that's why the pi 1 of 1 plus this. Okay, so we have reflections and we have concatenations, and that's sort of what we need to define the next important operation on paths. So this is somehow the heart of the whole theory. These are called root operators. So they are operators on paths. So let's define what the root operators are. So it's a slightly long definition, so you'll have to keep track of the different parts of the definition. Okay, let's see, I have okay. So what are the root operators? So various things. First, there are two kinds of root operators for each simple root. Okay, so first let's give them names. So EI and FI. This is how we'll denote our operators. So what are these? So what is I? I runs over all the simple roots. In other words, I runs over the indexing set of the simple roots. So there are two root operators for each simple root. Okay, they're called EI and FI. Now EI is called the raising operator and Fi is called the lowering operator. So this is the ith raising operator if you wish, and this is the ith lowering operator. Okay. So I have these guys. Now they act on paths. So how do we so let's define one of them first. Let's start with EI on a path. So let pi be a path. So let pi be a path starting at the origin, piecewise linear. Okay. Take such a path. Now let's define EI pi. So to define EI pi, we have to do something. We first need to study another function. So in order to define this path, we first study the function, the behavior of a certain function. So let's call this function h sub I. Okay. This is a function which depends on the path pi as well. So I'll call it hi pi of t. So function of time is defined as follows. It's just I take my path pi t and I evaluate it at alpha I check. There I'm going to define them. So we will now define, okay. So I'm going to define the EI and the Fi. First the EI. So let's define EI. So like I said, to define EI, in fact also to define Fi, this function is an auxiliary function. We first need to sort of study the behavior of this function, and the EIs and Fis will be defined based on the behavior of this function in some sense. So what is this function? So first, how does it make sense? Pi t is an element of h star, right? So it's an element of the dual of the Cartan. Alpha I check is an element of the Cartan. So it makes sense to evaluate this on that, pi t of alpha I check. Now, so what sort of function will this be? First thing, this will certainly be a piecewise linear function. So what are the obvious properties of hi pi? This will be piecewise linear. I'm sorry, what? Oh, excellent. That's the other thing I was going to say. Let's figure it out. So remember, t is ranging only over what we call as 0, 1, which means the rational numbers inside 0, 1, right? So I'm only looking at the rational entries, and pi of t was an element of pq, right? Where does this belong? By definition, this was an element of the rational span of the weight lattice, okay, for every rational number t. Okay. So that evaluated at alpha I check. So if you remember what the weight lattice was, the weight lattice evaluated on alpha I check always gave you integers as answers. That was the definition of the weight lattice. Now the rational span on this will just give you rational numbers as answers. Okay. So this is in fact a rational valued, piecewise linear, rational valued function. And again, I mean, always the key thing is t is only being allowed to take rational numbers. I mean, even though we keep drawing these as continuous curves, we are really only allowing t to run over the rationals in some sense. Okay, so let's draw this function. It's a piecewise linear rational valued function. Now before that, let me draw this path pi. Okay, what is pi as well? So I'm going to draw two things now. I'm going to draw the path pi, and I'm going to draw this function hi pi of t. Okay, so let's draw both of these things. Okay, so maybe we will get rid of this. In fact, let me just erase this as well. I'll just write this definition out again. Okay, so first let me draw the path pi. So here's the path pi. So it's supposed to be a piecewise linear path. So it starts at the origin. So imagine I'm drawing it on the plane. At the moment the plane is my h star. Okay, I'm going to draw this path on the plane. So here's my path. I mean, can also self-intersect and so on if you wish, but for, okay, this is the end point of the path. Okay, the path ends there. So I just drew some random path. This is a piecewise linear path, okay, with sort of 9 segments, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, it has 9 segments. So this is a path inside H star. So all this is a picture of H star. Okay. Now on the other hand, let me draw that function hi pi of t, which by definition was I need to take each point on this path pi of t, typical point, it's an element of H star, evaluate it on alpha I check. Okay. So I've gotten some rational number as we said. Now let me plot this guy. Of course, now when I'm plotting this is just a function of a variable t, that's all. So now I'm plotting a graph. Okay, so now I'm just going to plot the graph of this function. Okay, so plotting graph just means t runs from 0 to 1, wherever that is, and along the y-axis I will plot the value of this function, that's it, hi pi of t. Okay, so again it's going to have, just like, since my original path had these 9 different segments, linear segments, this function hi pi will be linear on each of these segments, right? Because I'm just evaluating the value pi t at alpha I check. On this segment, the path looks like, let's say, some linear function of t. So therefore, when I evaluate it on alpha I check, I'll just get some linear function of t. Okay, so on each segment here, I will have a corresponding linear segment in my hi of t. So let's draw that. Let's say it looks like this. Okay, how many segments did you get? 1, 2, 3, 4 so far. Say this is 4, 5, 6, 7, 8, 9. Okay, so let's say that this is how the graph looks. Fine. This is just for each segment there, I have drawn a corresponding segment. Fine. Okay. Now let's define what the operator ei will do. Ei, remember, will act on the path. Okay, it will act on the path depending on something which we will find out from here. Okay, that's the thing. That's why we sort of need both pictures at the same time. So what's the definition? The first thing it says, take this function and find its minimum value. Okay, step 1, find minimum value. So in this case, for example, this function attains a minimum. So let's say, I intended this to be the same value. So let's say the function attains this minimum in 2 points, let's say here. But to define ei, so okay, so let me first mark the minimum here. So I first mark the minimum value. Okay, I'll call it mi of pi, the minimum value of this function. Okay, you first mark the minimum value on this guy. Now, if this minimum value is not negative enough, okay, so first step, if this minimum value mi, so step 0, mi pi is defined to be, I can't see anything here, mi pi is defined to be the minimum value of hi pi of t as t runs over that interval. Step 1, if this minimum is too large, by which we mean if it's any number which is strictly bigger than -1, okay, then you say that ei pi is not defined. Then ei pi is not defined, but usually it's convenient to just do this. We say ei pi is 0. Okay, so really what we mean is not defined. This is just shorthand for that. This is just Okay, when it's not defined, we'll just say ei pi is 0. I mean 0 is just thought of as some path, you know, which doesn't exist, if you wish. Okay, so it's not defined in that case if the minimum value is strictly bigger than -1. Now, if the minimum value is low enough, it's -1 or lower, then here's what we do. Okay, so here's the definition. So I'm just going to sort of tell you the definition in an informal sense where it makes sense, but in the tutorial we'll actually write this out in sort of more formally, mathematically, and so on. So here's what you do. You take this minimum value and imagine you're doing the following. You shine light on this diagram. Okay, when I say you shine light, so you sort of take a torch light from the left. Okay, so you shine light on this diagram from the left. Okay, and how big a beam of light? You pick a light beam of width 1. Okay, and align it with the minimum. So I start with the minimum and go as far as minimum plus 1. So let's say this is minimum plus 1. So here's my light beam, minimum till minimum plus 1. Okay, I take a light beam of width 1 and I shine it on this diagram. Okay, now I then study what happens. So when the light falls on this, I look to see which portions of the graph are illuminated. Okay, so let's ask which portions of the graph are illuminated. So the light falls like this. So you can see this part of the graph is going to be lighted up. Correct? Now this mountain here is in the shadow, right? The light can't reach this portion, and then again there is a certain other part of the graph which is illuminated, which is the portion below this, you know, below this line, right? So when I shine light on this, there are exactly two parts of this graph which are illuminated, which is this portion and this portion. And none of the other portions of the graph will have any light on them, right? Anything to the right of that minimum won't, anything above won't, because the beam is only supposed to have width 1. Okay, so shine light, find the illuminated portions. So this is step 2, shine light from left, beam between mi and mi plus 1, okay, and mark the illuminated portions. Okay, so this is the bit where we need to study. This is what we mean by studying the graph HI. What we do with the graph HI is just shine light and see which parts of the graph are illuminated. Okay, now the job of HI is done. We go back to the original path pi, right? Here's the path pi. Now the portions of the graph that are illuminated here actually correspond to some parts of the path, right? So this corresponds to some time. So from time 0 till that time t, the graph is not illuminated. From this time t, whatever this is, till the next time t here, for this time interval, this graph is illuminated. Then similarly later on, for some subsequent time interval, the graph was illuminated. Correct? So I figure out what those time intervals correspond to in this graph. So for example, the first segment, this is the fag end of the second segment. So the first segment is not illuminated. The last bit of the second segment, somewhere here, this is illuminated now. This corresponds to one part of the graph that's illuminated. And there's one more like that, which is not in the third, but in the fourth, right? Third, fourth. The fag end of the fourth segment is illuminated. Okay, so this graph is, there are two segments which are illuminated. The rest are dark. Okay. So now we are ready to define EI. So here's the definition. Split up the path into the lighted and dark portions. So split the path pi up into the lighted and dark, into a concatenation. So you think of it as a concatenation of smaller paths. So smaller in, I mean, you sort of know what I mean by that, you know, some subset of pi. So smaller paths in which each segment is, you know, which is entirely lighted or dark, which are wholly lighted or wholly dark. Okay, it's a royal pain to write these things out. What is meant is much more trivial to see from the diagram. So what is meant is you split this path up such that each path that you write should be either fully dark or fully bright. You shouldn't have mixed segments. So what is meant by that? So I split this up as follows: from 0 till this bit, that's one segment, one path. I'll call this path pi 1. Okay, this is the dark, this corresponds to one dark portion. Then I have a one bright portion here. That path I'll call pi 2. Okay, then again I have a dark portion of the graph which corresponds to this, That portion of the graph I'll call pi 3 of the path. The illuminated portion here is called pi 4. And the rest of the graph is, rest of the path is dark, so we'll call that bit as pi 5. So here we split, it's enough to split into 5 bits. Okay, and this last path we'll call pi 5. Okay, so we have written the path out in this case as pi 1 concatenate pi 2 concatenate pi 3 concatenate pi 4 concatenate pi 5. So that's what this step means. So I have now written pi as follows. Okay, you write it in that manner, and then step 4 then says what ei pi is. Ei pi then is defined as follows. You look at these bits, it's just pi 1 dash concatenate pi 2 dash star pi 5 dash, where what does dash mean? Where for a path pi k, pi k dash will just mean the original path if it is dark, and not the original, but so maybe I'll do it in general. For any path eta dash will just mean the same as eta if eta is dark, and si of eta if eta is illuminated. So is this? I'm sorry, what? For any path eta, this is my definition of prime, if you wish. Eta prime will mean, I mean, this is for the ith. I don't want to overload the notation with another I and so on. So I'm just doing the ith raising operator. There I'll mean eta prime will just mean it's the same as eta if eta is dark, but it is the reflection si eta if eta is bright. Okay, so the green portions of the path, in other words, are left unchanged, whereas the yellow portions of the path have to be reflected by si. Okay. What? Right. Okay. So you see my definition of concatenation. So I need to unravel that. You had a question? What? Yeah. This one. This one here? No, just think of it as a mountain, right? See, I have this, I have a mountain here. So when light falls on it, this is in the shadow, no? See, this bit is in the shadow of this. So actually think of it as, you know, an actual physical thing there. If light falls on it, it's not going to allow light to pass through. So this line will not allow light to pass through, if you wish. It's opaque as far as light is concerned. It can't pass through it. Yeah. Okay, so concatenation, coming to, so we need to unravel just one more thing here. What is meant by this splitting into many bits and then, you know, doing some operation on some bits and then pasting them back again? That's what this concatenation means. So remember what concatenation was. Concatenation meant I have two paths, both of which start from the origin. So let me do this here. So I have one path pi 1, let's say, and I have another path pi 2. Both start from the origin, right? All paths are supposed to start from the origin, in fact. So when I concatenate, I always shift the start point of this path to coincide with the ending point of that. So the concatenation just means this guy, right? So now what we are doing when we split the path up into many bits is, I mean, it's not, now we are translating everybody to the origin. So when I say split it into many bits, pi 1 is this path, pi 2 is not quite this path which lives here, it's a translate. I have to move pi 2 to the origin such that it, you know, my labeling this as pi 2 is slightly misleading. That's not quite pi 2. Pi 2 should be this path but thought of as beginning from the origin. So this is really my pi 2. Similarly, this path here which goes like that, that's not pi 3 really, but it's this guy beginning at the origin, that's my pi 3. This is my pi 3 and so on. So I have to shift all paths back to the origin because that's how I'm thinking of my paths. So that's when the concatenation, see, I'm writing this as a concatenation of pi 1, concatenate pi 2, concatenate and so on. That only makes sense if, you know, pi 2 is this path, right? I mean, also my definition being all paths have to start at the origin. That's how I'm supposed to consider. Those are the only paths I'm considering. And so now reflecting a path now means the following. When I have, say, this portion pi 2, so I translate pi 2, I mean I move pi 2 and I mean this is really my pi 2, right? This is actually my pi 2. So when I say reflect pi 2, so reflection will do the following. It will move pi 2 to, it will reflect it about that hyperplane, right? So when I reflect pi 2, maybe I get something else. Let's see, maybe this is what it becomes. How should we do this? So let's say this is the reflection of pi 2. Okay, this path here is Si of pi 2. This is what I get when I reflect. Okay, so suppose that's the reflection of pi 2. Then what is my new path? What do I get after I apply Ei? So let's try to work that out. So maybe I should not try to do everything the same origin. So let's draw pi 2 and Si pi 2 on a separate origin. So let's imagine this is the origin now, and let's say my path pi 2 is this, and its reflection looks like this. So this is, let's say, Si pi 2, and this is my path pi 2. Okay, so now what does this concatenation mean? So first I traverse pi 1. Okay, so pi 1 dash is just pi 1. So let's do it in this particular example. So what is Ei pi therefore? Pi 1 dash, so Ei pi in this example is pi 1 dash is no change, that's pi 1, Si pi 2, nothing happens to pi 3, pi 4 gets reflected, and nothing happens to pi 5, right? This is my Ei. That's what's happening. Those two bits are alone getting reflected. So let's figure out what that means. So pi 1, now pi 2 reflection, I have to replace this segment of the path by its reflection. Okay, so instead of pi 2, I need to do this. I need to change my path. It now becomes this portion. It's now Si pi 2. Okay, so the path now is this, followed by this blue segment. Now, what happens to the rest of the path? So pi 2 is gone. It's instead become Si pi 2. Now what happens to pi 3? Right, remember this is not pi 3. Pi 3 is actually this fellow beginning at the origin. that has to be concatenated to whatever I have until now, which means its origin must be brought so as to coincide with Si by 2, right, to the origin there. So therefore, what I have at this point will just become, this guy, but starting from this point, right? So that's my new fellow. So I don't know. Let's say that's my new. That's what I get after I concatenate it with this. Okay, that's my new pi 3 if you wish. Okay, so I mean, if this, I hope this labeling it as pi 3 is not confusing you overly. I always, when I say pi 3, I really mean it's this path thought of as beginning at the origin, but now I have concatenated it, that's all. So now concatenating it will again mean that this and this are not in the same, right? This path is sort of broken again, but that's because pi 4 actually means this path. So pi 4, let's say, is this path starting at the origin, and the reflection of pi 4 along Si may be something else. So this pi 4 probably reflects, let's say it reflects to this. Let's say this is Si of pi 4. Okay. So which means I should replace this pi 4 by this Si pi 4, but beginning from this port, this bit. So this is my Si pi 4. So I erase this bit. Okay. And finally, this, whatever is left of the path, that should begin from this point. Okay, I just move everything, shift it down so that it begins from there. Okay, so that's the last bit of the path. So that looks like this, 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 and this. Okay, so let me get rid of the original path. So this was my original pi 5. Which I have replaced by this other part. Okay, so this is my pi 5 after its translated. So is this fine? So this is the final definition. So this is Ei acting on the original pi. Okay, what it's produced is some other path, right? What some portions of the path remain the same. Pi 1, pi 3, and pi 5 are actually the same as the original, but some two intermediate segments got reflected. Okay, and then you have to cut, reflect, paste back. Okay, so it's, in that sense, it's a slightly involved definition. Now the bits that you have to, which are the bits that need to be reflected. In order to identify that, that's where you need this HI, this auxiliary function, and this whole light shining and so on and so forth. But like I said, if you're slightly unhappy with this whole light shining business, we will actually write it out formally as a mathematical thing. It has a very compact expression. You can just say it is, a certain min of a max or a max of a min and so on. Okay, so it's not all that hard. Okay. Why it is not defined? What? Right. Some portion will go up. Yes, that's right. So I mean. So one answer is, if you think of this beam of light, if the minimum is greater than -1, it will sort of, some part of the beam will be on the top, right? But I guess that's not an answer. You have a, why would you not want to define this? So I suppose it comes from. So in some sense, this is supposed to be the, such paths are the highest weight paths, whatever. So finally, I mean, all this is supposed to tie in with the representation theory, right? So there, the highest weight paths in some sense are the ones which you cannot raise anymore, they are killed by all the EIs. So this is some reflection of that. There are, you probably saw this today, right? The what? No, what increases by 1? Final weight increases by 1 is okay, but see, that will probably still happen, right? If you have I see what you mean. That will not happen if you have this. Okay, makes sense. That's another way of thinking about it. So see what Venkatesh is pointing out. So maybe that will get answered as soon as I talk about the next property. Absolutely. So there is actually a good reason why this will not happen. So what you want is, see, EI, when I say it's a raising operator, in what sense is it raising? What does it do? Okay, it raises something. That's why it's called the raising operator. What it raises is the endpoint of the path. Okay, so this endpoint of the path, in comparison to the original endpoint. So I don't know, where was the original endpoint? Here, right? This was my original endpoint of the path. Now this is my new endpoint. Okay, so what it's done really is it's changed the endpoint. This original endpoint got moved to some new endpoint. Now this change is going to be exactly plus alpha I. What it's going to do is it's going to raise the endpoint by the amount alpha I, by the amount of that simple root alpha I. That is the sense in which this is the raising operator corresponding to the simple root alpha I. Okay, so this endpoint changing is by this amount plus by exactly this amount alpha I. This goes up by alpha I. And this will not happen if your minimum is greater than -1. Okay, because when you sort of shine light and so on, you will not be able to illuminate a beam of width 1. See here, when you shine light, what's happening is the illuminated bits add up to a total depth of 1. Right? This decrease plus this decrease is exactly 1. Right? The entire, so the beam somehow does its job fully. That you are getting an illuminated portion of depth 1 in some sense. If the minimum is greater than -1 and you sort of shine a beam of light there, you see that this portion here, which lies above the x-axis, that much is going to be that's unilluminated. That's not going to lead to any illuminated bits. Okay, so there you will lose a certain amount of this. So anyway, it'll probably be a little clearer when I talk about that property. You won't find this raising by that amount. Okay. See, the other thing is that the illuminated bits, you always want them to be going down. Okay, these are the down bits, and you raise them in that sense. If you think of trying to do it this way, I mean, in some sense, this portion here, which is going up, is going to get illuminated. Right? A little bit of the graph which is going up will be illuminated. And that's where part of the problem will arise. You won't get this property at all. Okay. So anyway, so all this is hopefully will become clearer as we talk about the definition. So let me stop at this point and ask: is the definition of EI clear? It's rather complicated, but the final idea is rather simple. Okay. Cut based on which portions are illuminated, reflect only the illuminated portions, and paste everything back. Okay.
Is the change of the EI interesting?
Yes, it's important also, absolutely. We'll do that in a second. But before that, let's now do Fi. Okay, so we have talked about the raising operator, which is EI. Now let's do the lowering operator Fi, because it's absolutely no work. We just have to change I don't think anything else changes. Okay. So how do we define the okay, this bit has to change. So let me just change this bit of the thing. So how do you define Fi? Fi pi is 0 if something happens, if what happens. So now the idea is you have to shine light from the right rather than from the left. Okay, and shining light from the right again means, so let's remove the EI bits now. So here's the minimum. Notice that the minimum, as in my diagram I said minimum is attained in two places. Okay. Now when I shine